Aloha. Welcome back, everybody. I hope everybody is continuing to do and be well. Doing my little part here. I got little Herman, the hermit crab, here helping me out. A little emotional support, so I'm not just alone in this room. Give it another week or two, and me and this dude will probably be having pretty good conversations. Think, what you call it? Tom Hanks' Castaway, right? Wilson, Herman, what's the difference between bulk density and particle density? Herman, right? Great. Okay, so we're gonna go get through the second half here of soil physical properties. Talking about particle density, bulk density, and porosity. Quick house cleaning. Since the amount of material we've gotten over since this transition isn't too much, we'll do a live Zoom meeting next week, Wednesday, at the lab time, and I'll provide that information on Laulima on how to get on there. And what else do we have? Oh, yes. So I put up discussion tabs on Laulima. I'll be putting them up for each video. Okay? So there's on one for the last one. I don't know if a notification went out. There'll be one for this one. I will put a notification out. And then so you all can, if you have any questions, comments, what have you, feel free to post them there. I'll keep tabs on that and can answer questions as needed and everything. And anytime, please don't hesitate to contact me. Probably via email is the most efficient. Okay, nkruger@hawaii.edu. And as we move along here. Okay. All right. In an effort to keep these videos somewhat not a million years long, we will get right at it. All right. So, very important distinction to start off with. We mentioned before. We talked about bulk density a number of times. So, a couple of distinctions between bulk density and particle density. Bulk density is dealing with the mass per volume, right? Both measures are mass per volume. Remember when we say bulk and bulk density, that means that we're also counting the airspace, the air, right, in there. We're just chopping a core of soil out of the ground, raising it up, and weighing how much mass in a given volume, airspace included, right? We're not jamming everything down and then seeing what it is, right? We're just as it sits in situ, okay? And not only that, but the physical components, the non-airspace components of bulk density are generally all kinds of different particles, right? We'll have kaolinite, we'll have some sand, right? Depending on where we are, we'll have allophane, we'll have organic matter if we're in histosols, allophane and andisols, for instance, okay? And so bulk density just takes all those different particles, just takes up all their mass. But an important distinction is that different particles of different substances, i.e. kaolinite, organic matter if we're in histosols, allophane, right? Gypsum, dolomite, magnetite, goethite, microclays, albite, quartz, right? All those different particles all have their own respective given masses for a given volume, right? So for the same volume of all these different particles, okay, types of mineral, etc., we have different masses, actually. They weigh different amounts because they're made up of different atoms, right? So, bulk density, we're looking at a soil core, undisturbed, right? And we're counting the pore space and air, and we're measuring that mass per given volume. Particle density, we're talking about individual, as I mentioned, individual particles of individual kinds of mineral, okay? And their given mass for a set volume. So for instance, right, quartz, we have here about 2.6, which is also kind of our standard, right, for this is in grams per centimeter cubed, okay, centimeter cubed, little die, right? So as you can see, pure quartz, right, has 2.6 grams per cubic centimeter, whereas soil organic matter, or just organic matter, if we're talking about a histosol, right, only has a particle density, right, 1.2 to 1.5 grams per cubic centimeter. So what, right? The types of particles present, right, that are going to contribute to bulk density, okay? This is one of those just informational things that we want to be able to identify, right? If we're in a quartz-rich soil, right, we're going to be having higher bulk densities because the particle density that's making up a lot of that bulk density is going to be higher, heavier. Okay, and so here are some instances of different particle densities. Kaolinite, montmorillonite, right? 1-to-1, 2-to-1 clays. Our allophane has a relatively lower particle density, right? 1.9 gram per centimeter squares, whereas kaolinite and our reference base of quartz particles is 2.6. Okay, and so what do we know about andesols is that they have relatively lower bulk densities, right? Because a large portion of that bulk is made up by allophane, which is lighter, right? So peat moss, very light, 0.2 gram per cubic centimeter. Humus, about almost 1, right? And then we can just for representative means look at cement, right, which is even higher than quartz or kaolinite. All right, so just talking about particle densities, okay, of those different constituents, right? But when we have a soil, for instance, right, we generally don't have 100% kaolinite or 100% allophane soil, okay? That's why the numbers don't necessarily add up exactly, right? The bulk density of an andesol doesn't equal the particle density of allophane because allophane isn't the only thing floating around in there. So this is a nice reference, okay? We go all the way from peat compost in our histosols, andesols, uncultivated soils, right? Cultivated soils, clay and silt loams going to sandy loams and sands, right? Vertisols, compacted areas and glacial till areas. So here would be another question, Mr. Herman. Why would cultivated soils have generally, right? Generally, uncultivated, okay, forest grassland has a lower bulk density than cultivated ones. Why, Herman? Why? Well, mainly because of compaction, right? As I mentioned, when we take a soil sample to get bulk density, we're not jamming that soil down, right? We're just pulling it right out in situ. That's why bulk density is actually so hard to get, right? It's a difficult number to get because it's actually very difficult to undisturbedly, right, remove a volume, so a mass of soil out of a given volume. So when we have cultivated areas, cornfields, soybean fields, exactly right, we're having a lot of tractor traffic, essentially, right? Machinery traffic. And so maybe in those top horizons, a plow layer, etc., right, our bulk density will still be around a lighter one after tilling, right? But then we have, as we can see, our fragipans right here. Generally, that's what the layer that's generally under plow layers, okay? And so then when we take the bulk density as a whole, right, to a deeper depth, right, then we're getting larger bulk densities for cultivated areas because a lot of that soil has been compacted and we're still collecting soil to a given depth, right? Okay. All right, ranges of some bulk densities. All right, so we've mentioned hissozols and aerosols a number of times. So hissozols, obviously, right? They have a pretty good range in bulk density, but all very, very low. Okay, and that's because the main component of the bulk density in there is organic matter, right? But hissozols are almost completely organic matter many times. Okay, so very light, very fluffy, easy to cultivate once they're drained. Okay, although we're going to be depleting soil reserves quicker than we could dream of as we drain them and then allow all that that aerobic environment into that what had been anaerobic, right? And allowing all those microorganisms to get oxygen and then work on all the organic matter around them. And then our vertisols and then our anisols, which are dominated by amorphous materials such as allophane that have very low bulk density, right? We mentioned even just the idea of allophane. This can kind of make sense because they're hollow spheres, right? Of aluminum and silica coming together in these spheres with tendrils, right? So they're not as nice and compact, right? And therefore heavier, right? In the same amount of area as, say, a vertisol, which is dominated by 2-to-1 clays, okay? And then again, we look at our uncultivated to cultivated clay and silt loam, cultivated sandy loam, sands, and glacial till. So why does, Herman, sand have a larger bulk density than clay? If you'll remember, a little bit back when we looked at those two figures side by side that were sand grains and then clay aggregates, okay? If you'll remember that those sand grains were solid grains, right? And those clay aggregates were porous, right? Had a bunch of holes in them, right? Micropores, right? We've been talking about that forever, right? So those clay aggregates are higher clay, right? Clay and silt loams, right? Clay and silt loams are gonna form more clay aggregates, so you're gonna have more air pockets in them, right? As opposed to just a set grain of sand, okay? All right, to talk on pore space, I think I've mentioned it a number of times as we've been moving along, such as, macropores drainage and water infiltration, etc., and micropores water holding capacity, carbon storage, etc. So this is on your radar and clear and in writing, right? Our macropores are mostly consisting of air, because we mentioned that where does water hang out in the soil matrix in a bunch of soil aggregate areas, right? That are forming macropores, right? We've talked about the water films that occur along the edges of the different particles that are close together, okay? And so that water is mainly just along the edges of those pore spaces, right? And then in the pore space proper, we're dominated mainly by air, okay? And so macropores are generally connected, right? Think of just a bunch of boulders just clumped up all over each other, right? And how, for instance, a field mouse or a mongoose, right, could easily just cruise through big old boulders like this, just thrown in this room, for instance, to fill up, right? There's going to be a lot of space for that little mongoose to be able to cruise all around in, right? So they're connected. And so they're just like that little mongoose can go and cruise around to all of them, so can water and air semi-freely move. We talked about some of those differences of CO2 concentrations. So we have a larger kind of entrapment effect, but the macropores are generally connected, okay? Allowing movement of air and water, of course. That's where our water infiltration and percolation happens. They accommodate plant roots, okay? Micropores we have to get in our right zoom lens, okay? Our micropores are going to be generally too small to even allow little root hairs, or anything else access inside, whereas macropores, roots can generally freely move right around and set well. Okay, so in well aggregated clay soils, macropores are plentiful between the stable aggregates because a lot of those well aggregated clay aggregates can generally be up to about this, almost the size of a sand grain, right? If we remember our little picture, okay? So those big sand grains, just like, or those big aggregate size grains, I beg your pardon, similar to the sand grains, right? Or like those big old boulders in this room that the mongoose can cruise in and out of, okay? So, try to remember that generally, if we're talking clays, if it's well aggregated, if we have aggregation in clays, we will still have macropores, okay? In clay-dominated soils that have generally had a lot of disturbance, right, we can talk more than about micropores. So, micropores mostly water-filled, but water is not always plant available. So we generally have water still in the aggregate, right, in a little clay aggregate after permanent wilting point. Okay. They are unconnected, more little pockets, right, than channels. Okay, and they are not conducive to root growth. But what they do, a little thing I like to think about with micropores is that they can protect organic matter, because some organic matter can work its way into these micropores, or it was stuck there when the aggregates happened, right? And so those little aggregates can generally form a kind of organic matter crypt, right? Or like a bunker, for instance, okay? So that organic matter that gets stored in those little bunkers is safe from microbes, right? And it's safe, which means that it's safe from being acted upon by microbes and being turned back into CO2 to just be released into the air, okay? All right. Jeez. Another live thing that I would love to be able to see everybody's faces on, but I guess I can imagine what everybody's face might look like seeing a big old slide of numbers. Okay, this is very important, and I am going to want you all to be able to find the mass of soil on 1 hectare of the plow layer. Okay, so a couple things to recap. Bulk density, right, is a measure of mass per volume, okay? When we are talking about field scale things, we're generally talking about areas, okay? Hectares, acres, etc., okay? So we can very easily change, when we're talking on big field scale things, we can very easily change from an area, i.e. a hectare, into a volume, which we're going to need for to plug in bulk density and find our total mass, right? We're talking mass per volume. So we're looking at what the mass of a soil is on a field scale, okay? We need to have our depth, which is going to give us our third dimension, right? If we have a hectare, it's a square, right? All of a sudden, if we have a hectare down in the plow layer, plow layer is 15 centimeters, okay? 0.15 meters, right? All of a sudden now we have a volume, right? We have a pool. Look at a hectare large, 15 centimeter deep pool, right? And we want to measure the mass things in that pool. How do we do that? Okay? Well, we need to know the bulk density. We need to know how much mass is in a given volume, right? And then we need to scale that up to what we're talking about, okay? So, hectare is, right, 100 meters by 100 meters. Those metric folks are very sharp, very sharp. How many square feet is an acre? 43,560? That's right, Herman. Good reminder. Thanks. But we're generally talking in hectares because we're in the scientific community, right? So, 100 meters. Given a generic bulk density, 1.3, okay, and that the plow layer is 15 centimeters or 0.15 meters deep, right? And a hectare is 10,000 meters squared, 100 times 100. 100 meters times 100 meters, okay? Not bad. 100 meters, that's 100 meters is our area, is our hectare. 15 centimeter depth, 0.15 meter depth gives us our volume per hectare, okay? We have from up here that 1.3 megagrams per meter cubed is the bulk density of the soil we're working with. There are 1,000 kilograms in a megagram, as we can see here, okay? We want to get to kilograms, right? Let's talk about it so we remember our basic math cancellation, right? We can cancel out our megagrams, okay? And then when we see this through, we have 1.95 times 10 to the 6 kilograms. Can we put that in a number? I could probably do it if I was a little smarter off the top of my head, but I'll draw it out. Someone been taking my pens? Ah, yeah, kidding. There's one. 1, 2, 3, 4, 5, 6. That's right. 1,950,000 kilograms of soil per hectare. Now, me myself, you might just have been thinking, why in the Lord's name would we go through it? Why ever would we need to know the mass of soil in 1 hectare of the plow layer? Why? Okay, actually a number of reasons. So, a lot of times when we're doing field scale trials, right? Say we're doing fertilizer trials, okay? We might want to look at the difference between applying 100, 200, or 300 pounds of nitrogen per acre, per hectare, okay? On corn, for instance, right? What happens, and many of our nutrient recommendations come in that form, actually, okay? For most crops, right, you're gonna get nutrient recommendations that are saying X pounds of NPK per hectare or acre, what have you, right? What happens then when we want to go do a greenhouse trial, right? With plants in pots, huh? This is actually when this comes in. So if, for instance, we were looking at nutrient recommendations for sugar cane, okay? And it said, oh, we want 200 pounds of nitrogen per hectare on this sugarcane crop to get a good one. We say, great, and then we want to do a little side study in the greenhouse, also looking at growth, right? How are we going to apply nitrogen to those greenhouse plants in pots when we only have the nutrient recommendations per area, okay? Or per acre or hectare, right? 200 pounds of nitrogen per hectare or acre. by this, okay? We actually find out that there's 1,950,000 kilograms, right, of soil per hectare for this volume, okay? So then we can do a couple of things. We can either weigh out the soil that we're going to be putting in our pots, right, and have that be a set mass going into each pot, and then level out our nitrogen things going from hectare down to the plow layer, which is 1,950,000 kilograms, right? And then we say, oh, we're going to measure out 2 kilograms, right, of soil to put into these pots. Then you would simply find the ratio of 2 kilograms to 1,950,000, right? And find out how much nitrogen you'll have to put in for 2. Because if you had a recommendation that said put 200 pounds of nitrogen per hectare, then what they're saying is put 200 pounds of nitrogen per 1,950,000 kilograms of soil. Yes. Let me say that again. When a nutrient recommendation on a per area hectare thing is said, if we work out this math, then they're actually saying, when they say 200 pounds of nitrogen per hectare, they're also saying 200 pounds of nitrogen per 1,950,000 kilograms of soil. Great. So obviously, if we have a pot that we're only going to put 2 kilograms of soil in, that number is going to be tiny, 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 tiny. And that's generally the case because we generally put in, 10 grams, right, into a pot like that for a pot study like that. The other way, so you could go by mass, and the other way you could do it, if you had your bulk density still, just get your volume of your pot, okay? And transcribe it to meters, okay? Your 0.15 meters tall, 15 centimeters deep, or I guess that's 30. And then you get your pi r squared, right? And get your area that way. And then you have your volume, right? Which is similar to a hectare to a 15 centimeter depth. You just do your depth and then your surface area, right? And get your volume. And then measure and then balance it that way, okay? So, we can see some real differences, right? 4.5 times 10 to the 5, so 450,000 kilograms of soil per hectare down to the plow layer for a histosol. And look at this, almost half for an andosol. Bulk density is almost half, right, of a standard soil. Okay. Oh! Nice little list of things, okay? Please look through some of these. Not everything here is just dished out clear as a bell in the material. I need to give some thought on some of these. This would be a good instance, more than likely, to utilize the discussion tab on Laulima if you so desire. If you have any questions on any of these, then please contact me. Please list it on Laulima. And I'll be getting a few more of these up. You know, whenever I put a video up, I'll put a notification on Laulima because it probably isn't going to exactly coincide with class time, okay? When we get into the live Zoom meetings, that of course will, right? But for these, I doubt that they'll just be Monday 11, Wednesday 11, okay? So I'll probably be putting them in, but I'll put notifications out for all of them. All right, mahalo, thank you all very much. continue being well, and we will talk again shortly. Aloha.